Welcome back, and this is the part of the channel where I go through a past exam question. This question was worth 5 marks. It did feature in an IB paper, but you would see this in an AP Calc or A-level course as well. It involves finding a derivative and then also locating a local minimum point. Let's get started. Okay, so we have about 5 minutes to solve this if it's worth 5 marks. Start the clock. Consider this function, where x is an element of R. The graph has a local minimum at point P, Q. Right, find the value of P and Q. So therefore, they just want us to find the coordinate of the local minimum. Right, we're going to start off with the function f of x is equal to 4x cubed over 3 minus 16x. And we're going to use the power rule to find the gradient function. So we're going to multiply by the power and take one off. So those 3's would actually cancel, leaving just 4x squared. Minus 16, and I want to equate that gradient function to 0 because remember a local minimum has a gradient of 0. So what we want to do now is solve that. So we're going to factorize out a 4 and have x squared minus 4, and that looks like it's the difference of two squares. So what I'll do over here is I'll just say, well, that's the same as saying then 4x minus 2 x plus 2. Right, so the gradient is equal to 0 either when x is equal to 2 or x is equal to minus 2. So we want to know which one of those is the minimum point. Well, what I'll do here is I'll use a combination of two things. Let's go ahead and use this gradient function now. And when you sketch the gradient function, that might tell me some things that will be very important to answer this question. So sketching the gradient function is, well, it goes through minus 16 on the the y-axis, and it is a concave up nature. So the gradient function would look something like this. Okay. Now, if we remember that this is the gradient function, so we want to know, is the gradient positive or negative in certain regions? Well, the regions that it passes through here would be minus 2 and 2. Those are the intercepts. That is because I found them here. That is when the gradient is equal to 0. Now, I just want you to focus on these major regions. So this region here, everywhere in that region, the gradient function is above the x-axis. So the gradient is positive in that region. Everywhere between minus 2 and 2, the gradient function is below the x-axis, so it's negative. And everywhere to the right of 2, the gradient function is positive again. So the gradient, if you want to think of it going like this, it goes positive gradient. Sorry, this is me doing a very crude sketch of the original gradient. So f of x would be positive, then we have a 0 gradient, then we have like a negative gradient, then a 0 gradient, and a positive gradient. And this is a very crude sketch, but it does give you an idea of what the shape of the original curve would be. And it looks to me like the gradient is, the minimum would occur here. And that would be when the value of x is equal to 2. Now, if you want to use a sign diagram, you can use a sign diagram. So I'll just briefly pause the video whilst I go through the sign diagram. They're super helpful. So let's say I drew a number line, and on this number line, I marked the points where the gradient was equal to 0. So let's say that was minus 2 and 2. So we just mark at the top here, gradient. So imagine the top part of this line is being gradient and the bottom part is being the value of x. Now what you can just simply do is test either side of those zeros. So I like to use the factored version here. So let's say we're going to substitute in a value to the left of minus 2. So let's just think minus 3. So you don't actually need to calculate the value, just look at the signs. So we would have 4 times a negative value, because minus 3 times minus 2 is minus 5. And this would also be negative. But then if we have a positive times a negative, that would actually result in a positive value. So to the left of this 0 will be positive. Now we're going to try a value between minus 2 and 2. So I'm just going to try 0. So if we go back over to here and we substitute 0 into this gradient function, positive times a negative times a positive. Right, so that would result in a negative value. And we'll just do the last one. Think of a value to anything to the right of 2. So I'll just pick 3. And I'll go back over to here, and we just do the same thing. 4 times a positive value times another positive value would be positive. Now, if you look very carefully, what we do is we have exactly the same setup as we had in the previous method, where if you were thinking about just the raw gradient from the original function, it would be positive, then it would be 0, then it will go negative, and then 0, and then positive. Now, I know there may be points of inflection and so on in there, but the main point is this is the setup that you want, where you have a negative gradient coming into a positive gradient. Therefore, that would also show you that that was the minimum point. So I just want to cover that because that is a very useful second method to find a minimum or a maximum. Right, so we have a gradient 0 and our minimum there is 2, but we need to find the y value because it wanted remember it wanted x and y. So we know that p is 2, but what is q? Well, let's go ahead and plug 2 into this original function here. So let's go up here. We have f of 2 is equal to 4 times 2, that's 8 over 3 minus 16 times 2, so that's 32. They've given us a fraction here to deal with. Okay, so we've got 32 over 3 minus 32. So we're going to need to times top and bottom by 3. So that'd be 96 minus 96 over 3. So the final answer there is going to be minus 64 over 3. So a bit of a nasty end to that question. Minus 64 over 3, and that is our value for Q. So minus 64 over 3, and we have found P and Q. Stop the clock. Let me know how you get on in the comments below. Don't forget to like and subscribe to the channel. See you next time.